Welcome back to the course Elementary Electrochemistry. In the previous class we have discussed about how to measure the EMF of a cell, and then from there I have shown you how one can determine the mean ionic activity coefficient using the EMF measurements. So today we are going to continue, and we will now discuss a few important aspects on how a cell is constructed and what are the meanings of some notations that I have been using over the last few classes. So today we will first talk about something called liquid junction potential. See, when we construct a cell, we use one line like this to separate the two solutions, and in some cases, if you have noticed, I have used two lines to separate the two compartments of a cell. So, for example, if I write zinc Zn 2 plus aqueous, one separation line with Cu2 plus aqueous with one separation line copper, writing it as plus and minus, and writing the same cell Zn 2 plus aqueous with two lines here Cu2 plus aqueous and Cu plus. So, these two have a slightly different meaning. So, when you write 1, it essentially means you have a semi-permeable membrane which allows for the passage of ions from one chamber to other, and that creates a certain problem. So, that is a junction between the two solutions, and because of that junction being semi-permeable, the ions can move from one side to other, but then a problem arises because of that. So, to overcome that kind of the problem related to that passage of ions and giving you an imbalance, one has to use something called a salt bridge, which is written as a double line. So, a semi-permeable membrane is written as a single line and a salt bridge is written as a double line. Why does it happen? Because the ions in the different compartments tend to diffuse through the junction and generate an imbalance. Why does that imbalance is generated? Because the speeds of the ions present in the solutions are not same, and as a result the faster ions move more across the junction or moves faster. So, as a result, one side of the boundary becomes positively charged and the other side slightly negatively charged. So, as soon as a charge separation takes place, immediately an electrical double layer is established. So, what happens because of that double layer, that the attraction of the two opposite charges prevents any significant separation of the cations and the anions. So, as a result, at the junction of the two electrolytes, a potential is developed, and this opposes the potential of the cell. So, this potential is called the liquid junction potential, right. So, this liquid junction potential, which is created inside the cell between the two electrolytic solution, cannot be determined using a potentiometer, and it prevents the passage of ions after it is developed, and hence hampers the electrochemical cell and it affects its actual cell EMF. So, to overcome this, one has to use something called a salt bridge. This liquid junction potential is represented by this symbol. So, what we use is called a salt bridge. So, what we use is a saturated solution of KCl or NH4NO3 in between the two electrolyte chambers. So, there are different ways of making it. You make an U-shaped bridge filled with the saturated solution of KCl, and sometimes some gel like agar-agar is used to hold that saturated solution of KCl in this. So this technically establishes the electrical connectivity between the two solutions, which are then connected with the corresponding electrode. Suppose this is copper, this is zinc, you have Zn2 plus here and Cu2 plus here. So like that, when you have a salt bridge connecting the two sides, then it does not allow to the generation of the charge separation, because the speeds of the cation and the anion present in the salt bridge has the same ionic mobility or ionic speed. As a result, the imbalance is not created across the salt bridge. So when, as I already indicated, when the salt bridge is used, then the corresponding cells are written like this, as I have written for zinc 2 plus aqueous is in connection with Cu2 plus aqueous with with Cu as the electrode. Similarly, one can have Zn in equilibrium with Zn2 plus in aqueous medium. Then on the other side, one can have 0.1 normal KCl solution, which is then in equilibrium with Ag2Cl2 solid and mercury liquid, which is calomel electrode. So then again you have a salt bridge to eliminate the liquid junction potential that may develop between the two. And similarly, one can also write another electrode. Just for example, I am writing cadmium in touch with Cd2 plus in aqueous medium is now in equilibrium with Fe2 plus Fe3 plus system in aqueous medium with a platinum electrode. So in every case you have a salt bridge which eliminates the possibility of development of liquid junction potential. So for a salt bridge the potential of liquid junction is 0 and it is thus eliminated. So using salt bridge we can avoid a potential problem which gets generated because of the variation in speed of the ions present in the two different compartments. So now we have already discussed little bit about different types of cells. One of them we now need to pay attention is a cell which is called a concentration cell. As you know, in general, the EMF of a cell is a consequence of a net chemical reaction taking place inside the cell. But it is also possible to generate EMF out of a cell without any net chemical transformation. If such a cell can be constructed, those are called the concentration cell. Why? This happens, this EMF the EMF of a concentration cell is a result of transfer of ions from one compartment to the other in the cell, right? So there are two types of such cells. Let us first talk about the amalgam cell. Where two like or same electrodes are used with different activities and are dipped in the same solution containing an ion of the electrode material. So what essentially means that if I just want to give an example, silver amalgam with activity of silver as A1 is dipped in a solution of AgNO3, and on the other side you have another silver amalgam electrode with activity of Ag equal to A2. This is plus and that is minus. So the reaction that is happening on the left hand side is Ag getting oxidized to Ag plus and releasing one electron. What is happening on the right hand side is Ag plus taking an electron getting reduced to Ag. So there is no net reaction. If you add this, there is no change in the chemical composition of the electrode system. So there is no net reaction in this particular cell. But then when you write the cell EMF, you will write E left oxidation minus E right oxidation, as we have learnt in the previous class, and then we slowly write the corresponding Nernst equations. Then what you will get is E0 Ag minus RT by F ln activity of Ag plus divided by activity of Ag, that is A1, minus E0 Ag minus RT by F ln Aag plus divided by A2. So, now you see that this E0 Ag gets cancelled, this minus minus plus, so we write RT by F ln Aag plus by A1 minus RT by F ln Aag plus by A2, and when you simplify you end up getting RT by F ln A2 by A1. So, here what we are getting is that the value of EMF for this cell is regulated by the values of the activities of silver on either side. So, what is happening is there is a transfer of silver from left hand side to the solution of AgNO3. So, Ag gets converted to Ag plus here, and that Ag plus gets converted to Ag on the other side. So, there is a net transfer of silver from left to right, and that transfer is controlling the EMF of the cell. So, that is why this is a concentration cell where the difference in concentration gives rise in the transfer of silver ion from one side to the other, and it generates the corresponding EMF of the cell. The second type of concentration cell is a electrolyte concentration cell. So, here I am straight away writing one example so that you can understand easily. Suppose we have silver solid in equilibrium with AgNO3 aqueous with a molality M1, which corresponds to the activity of Ag plus as A1. It is connected to another solution of AgNO3 aqueous where the molality is M2, which means that activity of Ag plus on this side is A2, and you have again Ag solid as electrode, right. So, here what we have is we have on the two sides we have the same electrode, but we have solutions electrolytes of different concentration. So, here both the electrodes are same, but the concentration of the electrolyte are different on the two sides or the two chamber of the electrodes. So, when you try to write down the E cell like before, we will end up getting this expression E cell equal to RT by F. I am again writing F because again here it is one electron transfer, ln activity of A2 by activity of A1, right. Here I made a mistake, you should check. See, this minus, so this is A2 and this is A1. As a result, this should be A1 by A2, right. So, in this case, you see the difference is that it is A2 by A1. So, in the previous case, the activity of the electrodes were different. So, in that case, the E cell was determined by RT by F ln A1 by A2, that is A1 of the left by the right, whereas in this concentration cell it is A2 by A1. If you do the derivation yourself, you will find it. So, now if A2 is greater than A1, E cell is greater than 0, that is positive, and that essentially means EL is greater than ER, which essentially means oxidation occurs at the dilute side and reduction on the concentrated side. That is, dilute side is this. So, there the oxidation takes place and EMF of the cell turns out to be positive. So, if M and gamma terms denote molality and activity coefficients. So, now if we replace the values for A1 and A2 using M and gamma, you can write E cell is equal to RT by F ln M2 gamma 2 by M1 gamma 1, or simply RT by F ln M2 by M1 plus RT by F ln M gamma 2 by gamma 1. So, now by knowing the concentrations in terms of molality and by determining the corresponding gamma using the previous expression that we have learnt, one can calculate the E cell for the concentration cells. So, I hope you are able to follow these topics, and we will continue from here in the next class, where we will discuss about some more applications of measurement of EMFs in practical life. Thank you.